Welcome to the Depth Dive. Today, we're getting into toxicology, science of poisons, really.
Yeah, but it's more than just poisons, isn't it? We're looking at its whole history, even the darker side, like chemical weapons, and also this issue of radioactive stuff getting out of control.
Exactly. We've gone through 5 key documents for you, covering the basics, the history, the weapons angle, and those radioactive risks.
Our goal really is to pull out the core stuff, the essentials you need to grasp, without you having to wade through, tons of dense material.
Right. So let's jump in. What even is toxicology?
Well, fundamentally, it's the study of how substances can harm living things. The first document we looked at really stressed how vital this is, practically speaking, for people in emergency medicine, for instance.
Makes sense. And the second one gave us the key terms: toxicology, toxicants, intoxications.
Right. A toxicant is basically anything that can cause harm, chemical, physical, whatever. An intoxication is, the actual state of being poisoned, the resulting health effects. And that brings us to that famous quote from Paracelsus.
Ah, yes. The dose alone makes the poison. Such a fundamental concept. It basically means anything can be harmful if you get enough of it, right? Even like water.
Precisely. It's
Yeah.
all about the amount. And
Ah.
within toxicology, you've got different branches. We mentioned clinical toxicology. That's the diagnosis and treatment side. Super important in emergencies.
Okay. And toxicity itself can be classified.
Yeah, mainly local, systemic, or mixed.
Hmm.
Local is harm right where it touches you. Think a chemical burn.
Okay.
Systemic means it gets absorbed, travels through your body, and causes problems elsewhere.
Uh-huh.
And mixed is, well, a bit of both.
Got it. And the intoxication, the poisoning itself, that can happen differently too, like fast or slow.
Exactly. Acute is usually a single short exposure with effects showing up pretty quick. Chronic is from lower levels, but repeated exposure over time.
And then there was delayed toxicity. That sounds tricky.
It really can be. The effects might not appear for days, weeks, maybe longer after the exposure. Makes it harder to connect the dots sometimes.
Wow. Okay, and then this idea of dose response, that sounds important.
Hugely important. It's about the relationship between how much of a substance you're exposed to and how likely or severe the effect is.
That's where LD50 comes in.
Yep, LD50 is the lethal dose for 50% of a test population, and ED50 is the effective dose for 50% of the dose that causes some defined effect in half the group.
So it helps compare how toxic things are.
Exactly. Helps quantify the danger. For stuff you breathe in, we use LC50 and EC50, looking at concentration in the air instead of dose.
Right, right. So we know what it is, but how does it actually do the damage, the mechanisms?
Ah, good question. That gets into toxicokinetics and toxicodynamics. Bit of a mouthful, I know.
Okay, let's try toxicokinetics. Is that what the body does to the poison?
You got it. Think of it as the journey. Absorption, how it gets in, like breathing, swallowing through the skin. Distribution, where it goes in the body.
Yep.
Metabolism, how the body tries to break it down, often in the liver. And excretion, getting rid of it, usually via kidneys. ADME, sometimes people call it.
Absorption, distribution, metabolism, excretion. Okay, so then toxicodynamics is the flip side. What the poison does to the body.
Precisely. This is the interaction at the cellular or molecular level. Messing with cell membranes, interfering with oxygen use like carbon monoxide does,
Yeah.
blocking essential enzymes, damaging DNA, causing inflammation, all sorts of nasty effects depending on the specific toxicant. It's complex stuff.
It sounds it. But understanding that whole journey, ADME, and then the actual damage, that seems key to everything else we're talking about today.
Absolutely. It's the foundation for understanding historical poison use, modern weapons, radiological threats, all of it.
Okay, foundation laid. Let's pivot to history. The third document took us way back.
Ooh.
Primitive humans and poisons. They weren't just avoiding them.
No, fascinatingly, they were figuring out how to use them. The evidence, like poison darts from the Bronze Age, and practice is still seen today in some tribes. It shows active engagement, not just avoidance.
So learning to harness nature's dangers pretty early on.
Seems like it. And then in ancient civilizations, this knowledge becomes more formalized. Mesopotamia, arsenic on tablets.
Yeah, and Egypt had papyri about snake venom. India's ancient texts, like the Rig Veda, mention poisons. China, too, with things like aconite in their early herbals.
It shows that as societies developed writing and structure, they started documenting this knowledge, both the dangers and potential uses or antidotes.
Then the Greco-Roman era. The document called it the politics of death. Sounds dramatic.
Well, it kind of was. Mythology is filled with poison plots, Eurydice, Circe, and plays like Medea.
Right, and even Hippocrates warned doctors against giving poisons in his oath, so there was an ethical dimension emerging too.
Definitely. A sense that this powerful knowledge needed careful handling, especially by healers. But then the Romans, they really seemed to use it politically.
Locusta, the poisoner, and laws against poisoning cropping up. People like Pliny and Galen were writing about poisons and antidotes. It was clearly a real issue.
A major issue,
Yeah.
which spurred not just laws, but also the search for effective treatments, like Galen's work on antidotes.
Okay, so after Rome falls, how did this knowledge survive?
That's where the exchange between Muslim, Jewish, and Christian scholars during the Middle Ages was absolutely crucial. They translated classical texts, added their own observations.
Like Al-Razi and Maimonides. Maimonides wrote a whole book on poisons.
He did. Treatise on poisons and their antidotes. It shows they weren't just preserving knowledge, but actively building on it, synthesizing different traditions, a real intellectual melting pot.
Then the Renaissance, learning revived, but also the Borgias.
Ah, yes, the darker side resurfaces. Criminal toxicology kind of hits its stride. The Borgias become infamous, and later you get things like aqua tofana, a notorious poison in the 17th century used for assassinations.
Chilling. But didn't Paracelsus live around then too? The dose makes the poison guy.
He did. So alongside the criminal element, the science itself was slowly developing. Paracelsus provided that key principle, and later the first actual book titled Toxicology appears.
And people started connecting chemicals to diseases, like occupational hazards.
Exactly. Bernardino Ramazzini in the early 1700s, groundbreaking work connecting jobs to specific illnesses, often caused by chemical exposure. He basically founded occupational medicine.
Wow. And then Percival Pott linking soot to cancer in chimney sweeps later that century.
Another critical observation. And by the end of the 18th century, you even see the start of animal experimentation in France to study these things. It's a long, winding, and sometimes pretty grim history.
It really is. Which, unfortunately, leads us pretty directly into the next topic, chemistry used deliberately as a weapon.
Yeah, the fourth document tackles this explicitly. And perhaps predictably, the inspiration came partly from nature animals using toxins.
We mentioned the Spartans using arsenic smoke way back, but even then, people tried to ban this stuff.
They did. There was a treaty in 1675, and the Hague Convention in 1899 tried to ban asphyxiating gases. An early recognition that these weapons were somehow different, more inhumane.
But those bans didn't hold. World War I, that was the big turning point, wasn't it?
Absolutely. Massive scale use. Chlorine at Ypres, mustard gas, horrific injuries, hundreds of thousands of casualties. It was truly industrialized chemical warfare.
Which led to the Geneva Protocol in 1925. That banned the use in war, right?
Yes, the use, but critically not the development, production, or stockpiling. That was the loophole.
So nations could still make them, just promise not to use them first.
Essentially, yes, and that promise was broken. Italy and Abyssinia, Japan and China.
And then World War II, Nazi Germany, nerve agents.
Terrifying developments, taboon, sarin, soman, far deadlier than the WWI gases, and of course the utterly horrific use of Zyklon B in the death camps. Not strictly warfare, but industrialized murder using a toxic chemical.
A complete perversion of science.
Unquestionably. And the threat didn't end with WWII. Newer, even more potent agents like VX and later Novichok emerged. These are classed as weapons of mass destruction.
And they've been used since.
Sadly, yes. In the Iran-Iraq War, by Iraq against the Kurds, in the Syrian Civil War more recently, and in terrorism, like the Tokyo subway attack with sarin, or assassinations like the Scrupple poisoning using Novichok, the threat is persistent.
It really is. The document also broke down the types. Neurotoxins, hemotoxins.
Right. Neurotoxins hit the nervous system. Sarin, VX. Hemotoxins affect the blood. Vesicants cause blisters, like mustard gas. Asphyxiants stop you breathing, like chlorine or phosgene. And then incapacitants, like tear gas, designed to disable rather than kill, though they can still be dangerous.
It's a horrible list. Understanding the types must be key for defense and treatment, though.
Definitely. Different agents need different approaches. Which brings us to our final topic, another kind of invisible threat, uncontrolled radioactive materials.
Right, the fifth document. Let's start with the basics again. Radiation. It's energy.
Energy released from unstable atoms. Radioactive materials contain those unstable atoms. The process of releasing that energy is radioactivity.
And there are different kinds. Alpha, beta, gamma.
Correct. Alpha particles are big, slow, easily stopped. Beta are smaller, faster electrons, more penetrating. Gamma rays are pure energy, like X-rays, but stronger, very penetrating. And then there's neutron radiation, typically from nuclear reactions. Different hazards, different shielding needed.
Okay. And what's the difference between radiation and contamination? I always get those mixed up.
Good question. Radiation is the energy traveling through space. Contamination is the radioactive material itself getting onto surfaces or into your body where it shouldn't be. Think of radiation like the heat from a fire, and contamination like getting soot on you.
Ah, okay, that helps. And it's ionizing radiation that's the main worry for health.
Yes, because it has enough energy to knock electrons off atoms in your body, which can damage cells and DNA.
And the effects, stochastic and deterministic.
Right. Stochastic effects are probabilistic, like cancer risk. The chance of it happening increases with dose, but there's no guaranteed threshold. Deterministic effects, like radiation sickness, do have a threshold dose, and the severity definitely increases with dose above that threshold.
I see. The IAEA, the International Atomic Energy Agency, they categorize radioactive sources.
Yeah, based on potential harm. Category 1 is the most dangerous, potentially lethal very quickly if mishandled. Category 5 is the least dangerous, unlikely to cause harm. It puts the risk into perspective. Most sources are used safely, but the high category ones are a major concern if they go missing.
Go missing, like orphan sources.
Exactly.
Yeah.
Lost, stolen, abandoned materials outside of regulatory control. That's the core problem.
And there are systems to try and find these. Detectors at borders?
Yes. Radiation portal monitors, handheld detectors, trying to intercept illicit trafficking.
Why would people traffic this stuff? What's the goal?
Several possibilities, unfortunately. Building an improvised nuclear device, a crude nuke, though that's very difficult. More feasible, perhaps, is a radiological dispersal device, or RDD.
A dirty bomb.
Exactly. Using conventional explosives to scatter radioactive material causes panic, contamination, long-term cleanup costs, health risks, or even simpler, a radiation exposure device, or RAD just hiding a strong source somewhere to deliberately irradiate people.
Grim possibilities. Who's doing the trafficking?
It varies. Could be individuals, criminal groups, maybe even state-sponsored actors in some scenarios. Sometimes it's accidental. Someone finds scrap metal unaware it's radioactive.
And if something does happen, nuclear forensics comes into play.
Right. Analyzing the material itself, its isotopes, impurities, age to try and figure out where it came from, who made it, who might have stolen it. It's like CSI, but with radioactive fingerprints. Crucial for attribution.
The document mentioned real incidents, stolen uranium, a dirty bomb attempt in Moscow.
Yes, these aren't just theoretical fears. The theft of highly enriched uranium in St. Petersburg in the 90s, the Chechens planting cesium in a Moscow park, threats against nuclear facilities, these underscore that the danger of nuclear and radiological materials falling into the wrong hands is very real.
It certainly puts it all into perspective.
It does. Proper security and control are paramount.
Okay, so wrapping this up, we've covered a lot of the basics of how poisons work, their long and often dark history, the specific horror of chemical weapons, and this modern threat from radioactive materials adrift.
From ancient poison darts to potential dirty bombs, it's quite a journey, showing how knowledge of potent substances has always been a double-edged sword.
Used for healing, sure, but also for harm, control, terror, and the challenges of regulating it all, especially the radioactive side, seem immense.
They are. It requires constant vigilance, international cooperation, and robust security cultures.
So a final thought for you, listening. We've seen this millennia-long story of humans grappling with toxic and radioactive power. Given that history and the dangers still very much present, what's our collective responsibility now?
Yeah, how do we, individuals, societies, governments, ensure these things are controlled safely in the 21st century? And maybe what new ethical questions will pop up as science keeps advancing our ability to manipulate these forces?
Something to definitely think about. Join us next time for another deep dive.